So the first topic we look at in A2 chemistry is lattice enthalpy. So looking at the title, you see the word enthalpy, which probably leads you to think that this might have something to do with the energetics topic we looked at in AS2, and you'd be right. Now, energetics in AS2 had lots of different parts to it, had lots of practical chemistry, had bond breaking, bond making, had Hess's law. It's actually only really the Hess's law part of energetics we're looking at here. We're going to use Hess's law in a wee bit more detail to work out and calculate the lattice enthalpy for particular substances. So most of this topic actually is only about one enthalpy change we're interested in calculating. So probably the first thing to look at would be what actually is the lattice enthalpy and why are we interested in it, and then we'll look at kind of the theory behind how we actually calculate it. So lattice enthalpy, the definition isn't on the first page, which we will look at, but probably easier if I just do a wee sketch first. What the lattice enthalpy is, again, you see the word lattice there. This is to do with ionic lattices, so things like sodium chloride, etc. So metals and non-metals bonded together. So remember back to your structures in AS1, ionic lattices are big 3D structures. We've got oppositely charged ions electrostatically attracted to each other. What we're talking about with the lattice enthalpy is an energy change or enthalpy change to split this lattice apart into individual gaseous atoms. So they're completely disconnected from each other. They no longer have an attraction to each other. So the energy to go from this stable lattice to these disconnected ions. Obviously it's going to take a wee bit of energy. This is an endothermic process because there's lots of strong attractions here. We're having to break those attractions here to get these split up. So that's what this topic's all about. The official definition, which you'll see in the first page, it's the enthalpy change when 1 mole of an ionic compound is converted into gaseous ions. So that's our ionic compound, here's our gaseous ions. That's fair enough. You might be thinking, well, why have we got a whole topic devoted to this one enthalpy change? Well, one reason is that the maths behind calculating it is quite interesting, it's quite clever. In terms of a use for it though, the lattice enthalpy in itself maybe isn't that useful, but we can use it to calculate things like the solubility of an ionic substance or the hardness of it. So it does give us some information about the properties of ionic compounds. So that's what this topic's about. It's about calculating this lattice enthalpy change. Now we're going to turn attention to how do we calculate it. We can't quite dive straight into any calculations because we have to do a wee bit of kind of definition work. As you might see in the next page, what the method used to calculate lattice enthalpy involves is lots of individual enthalpy changes being used together. That might not make much sense now, but will very shortly. So we need to actually have a little idea of a big range of enthalpy changes we might use in a calculation, in Hess law calculation. So on this first page, you see a big table of lots and lots of enthalpy changes. Again, you might not fully understand why we've got a big table of enthalpy changes, but for now, just let me tell you that it's going to be important that you understand what these enthalpy changes mean when it comes to our calculations. So first thing we're going to do is actually work down this list, make sure we're happy and understand what these enthalpy changes are actually describing. So there are 1, 2, 3, 4, 5, 6, 7, 8 on this list. Now the first 3 actually you have come across before. These are straight out of your AS2 notes. First one is your standard enthalpy of formation. Shorthand is delta FH. This is the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. So it's about making a compound, for example sodium chloride. On the left of the arrow you're putting the elements that make up that compound in their standard states. So sodium is a solid, chlorine is a gas. Have to make it balanced though. I'm only making 1 mole of the compound, therefore I use half a mole of Cl2 because it's diatomic. Normally it's endothermic. Normally you get a wee bit of energy out when you make a compound. It can be a little bit endothermic as well, but usually ectothermic. Next one is the first ionization energy, which you hopefully are very familiar with. We used it a lot last year, or in the AS topic. Shorthand you might not have used before, delta IE1 for first ionization energy. The energy required to convert 1 mole of gaseous atoms into gaseous ions with a single positive charge. And you should be very familiar with this equation form of it. You're making into the 1 plus ion, and you normally do show the electron in that equation as well. That's always endothermic because it always requires energy to rip a negative electron from its attraction to the positive nucleus. This third one is one you've come across before as well. We didn't really use it that much, but the second ionization energy is kind of the same thing as the first ionization energy. You're just doing it a second time. So it's the energy required to convert 1 mole of gaseous ions with a single positive charge into gaseous ions with a double positive charge. So you're going from Na plus to Na2 plus. Obviously, in the case of sodium, that's maybe not that likely a process to happen, but we're just keeping it consistent with the examples. But it's going from a 1 plus ion to a 2 plus ion with an extra electron. Same reason as before, it's endothermic. You're removing a negative electron from a positive nucleus that requires a wee bit of energy. So the first three are all AS definitions, we looked at before. The remaining ones are new ones to you, but that doesn't in itself mean that they're more complicated, they're just different. The first two we look at are called electron affinity enthalpy changes. Electron affinity, we'll look at the definitions. They are basically just the reverse of ionization energies. So ionization energies are energies where you're removing electrons from an atom. Electron affinities are the opposite. You're adding an electron to an atom. So the first electron affinity is the enthalpy change when 1 mole of gaseous atoms is converted into gaseous ions with a single negative charge. Might see it a bit more clearly in the equation. So if we take a neutral atom, like a chlorine atom, we add an electron to it, it becomes chlorine with negative charge. Exactly the opposite of removing electron to make positive. We're adding electron and making it negative. Generally speaking, that will always be exothermic, which might take a wee bit of thought. You are adding a negative electron to a nucleus basically with a positive charge, and that will generally give you out energy because you're forming a new attraction. In the same way we had the second ionization energy, we're doing the ionization energy twice, we also have a second electron affinity. So if you're starting with a Cl minus now, for example, you're adding a second electron to make it Cl2 minus. Now, so definition is pretty much the same, just it's changing a negative ion into a double negative ion. The one change that's important here is that that's now endothermic. So the first electron affinity tends to be exothermic because you're forming a new attraction. It's actually quite hard to add the second electron though. The reason for that is once you've added the first electron, you've now made your atom into a negative ion. If you then try and add another negative electron to an already negative ion, you've got a bit of a repulsion there, so they'll push apart from each other. So it actually involves adding a wee bit of energy to get them to stick together. So first electron affinity, exothermic. Once you get to adding the second electron, it becomes endothermic. So we've got our two electron affinity enthalpy changes. The final three are here. Now, I'm going to actually come back to atomization and bond dissociation in a second because they're a wee bit more in depth. Just going back to the one we started with, the standard Lattice enthalpy, which is what this topic's all about, the one we're trying to calculate. The definition of it is the enthalpy change when 1 mole of an ionic compound is converted into gaseous ions. So you're starting with, for example, sodium chloride, that's a solid in its normal form. You're splitting up completely into individual ions. So you see Na plus Cl minus. Notice the state symbols though. You're going from solid sodium chloride to gaseous sodium ion and a gaseous chloride ion. The gas bit implies that they're completely far apart from each other, so they're no longer interacting with each other. It's always endothermic because you're always breaking apart a strong, stable lattice. One thing just be careful about, don't need to worry about too much. The last enthalpy can actually be defined either way, and if you look this up online on Wikipedia or in a textbook, different places might define it actually going backwards. You can say the last enthalpy is the ions going back to the lattice, which would be exothermic. It doesn't actually matter either way. It just happens that SIA happened to define it as going from the lattice to the ions, which is endothermic. So we have to keep consistent with that. That's the way you should learn it. So I skipped these two because they're a wee bit more tricky, and they are a little bit more tricky. The enthalpy of atomization sounds a bit strange. Its definition is this: the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. The key bit there is you're forming gaseous atoms. That in itself might not be that tricky. The trickiness of this one is that can look different depending on what you're starting with. So we've got two different examples here which show that. So this is the enthalpy of atomization for sodium, and this is the enthalpy of atomization for chlorine. The key thing to focus on, and why they both count for atomization, is looking at what they finish with. In this top one, you're ending up with a single mole of gaseous sodium atoms, Nag, and in the second one you're getting the same. that's a single mole of gaseous chlorine atoms. So that's why they're counting both as enthalpy of atomization. The difference is where they're starting from. It depends on what the element is like you're starting from. With sodium obviously is a metal structure. So you're starting in a standard state as a sodium as a solid. So to get from a solid to a gas, you are effectively just melting it and boiling it. That's all you actually need to do. So if you break apart that solid structure into liquid, break apart the liquid structure into gas, that will be atomization. So you're going from this nice, neat solid structure, breaking it all apart into individual atoms. It's not actually the same for chlorine, no, because chlorine in standard state is already a gas. So it's not true to say that atomization is always just melting and boiling something. In this case, you got chlorine. It naturally exists as a gas, but it's a diatomic gas. So in this case, what we mean by atomization is actually breaking that bond between the diatomic molecule and make it into individual atoms. So we're really focusing on what you end up with. You're always ending up with 1 mole of gaseous atoms, but the difference can be where you're coming from. It might be a metal solid where you're breaking apart structures by melting it and boiling it, or it might be a diatomic gas where you're turning it into atoms just by breaking a bond down the middle. Either way, it's always going to be endothermic because you are breaking attractions, breaking bonds between things, so it does always require energy. Now, the second one is a little bit similar. It's called bond dissociation enthalpy, which we did technically use when we're looking at bond breaking, bond making calculations in energetics. This is the energy required to break 1 mole of covalent bonds under standard conditions. So it's only for covalent molecules, because that's in the definition. It's breaking covalent bonds, and it's breaking 1 mole of them. What that looks like is, in this example equation, Cl2, chlorine molecule, going to 2Cl. If you think about it, if I do over here, if I've got 1 mole of Cl2, so that's a diatomic chlorine, 1 mole of Cl2 contains 1 mole of bonds because there's 1 bond per diatomic chlorine. So my definition is the energy required to break 1 mole of covalent bond, I need 1 mole of chlorine to provide that. If I break that 1 bond though, I will make 2 individual chlorine atoms there. So it's just breaking apart that bond to make individual atoms. The reason I'm kind of going through this in so much detail is that this is probably the one area of confusion in this topic where they can deliberately try and trick you in questions to make you pick the wrong enthalpy change in a calculation. The confusion is specifically about things like chlorine. What you might notice here is that the enthalpy of atomization equation for chlorine and the bond dissociation enthalpy for chlorine are actually very similar. They both involve breaking apart Cl2 and making it into Cl. The difference is kind of the balancing numbers. With atomization, you're making 1 mole of chlorine atoms, so you need half a Cl2. But with bond dissociation enthalpy, you're breaking 1 mole of bonds, therefore making 2 moles of atoms. So one's kind of double the other one. They are kind of the same change, the same kind of process. It's just kind of the quantities to match up with your definitions are going to be different. So it might be worth taking down this wee note just to make that clear. Again, you might not fully understand why we're being so full on about these definitions. Knowing these definitions will make the calculations much easier for you. So the other thing at the bottom here, just about diatomic elements, because that's the only real place we can get this confusion. So diatomic elements. So for example, Cl2, I know I'm talking about Cl2 a lot, it could also be O2, F2, things like that. I'm saying we've got these 2 very similar enthalpy changes that could apply to both. We've got the atomization enthalpy, and we've got the bond dissociation enthalpy. Let's do BDE. What that means is atomization, remember, it's making 1 mole of atoms. So I'm making 1 mole of Cl. To make 1 mole of Cl, I'm going to use half a mole of Cl2 because there's 2 Cls per Cl2. With bond dissociation enthalpy, I'm breaking 1 mole of bonds, so I need 1 mole of Cl2 to give me 1 mole of bonds. If I break those apart, I get 2 chlorine atoms, or 2 moles of chlorine atoms. So one final time, these are obviously very close to each other, but they're slightly different. What we would say is the bond dissociation enthalpy, the actual value for that will be twice as big as the value for atomization because you have twice the number of chlorines involved there. So just to summarise that using our kind of wee code, so this is double that value. So using my shorthand, so delta BDE, the bond enthalpy, will be 2 times the atomization energy. And that's specifically for diatomic elements we need to worry about. Again, don't worry if you're not really sure why we're talking about this in so much detail. As long as you follow what I'm saying, that's the main thing for now. So we're about to go on to actually how we use these definitions to calculate the last enthalpy. Remember, this topic is all just about last enthalpy. But you might not believe me here, but if you actually spend a wee bit of time pausing the video and actually going over these definitions on the first page, I promise you will find this topic a lot easier. Often with definitions in chemistry, we kind of just leave them and say, just learn them for the exam. This one's a wee bit different. You have to understand the definitions to understand what to do with particular numbers and calculations. So probably worth taking a wee pause now, going through the definitions, and just make sure you're happy that you understand the differences between them and what they look like in terms of their example equations.